today's talk are the following. First, I would like to discuss about. I will give a recap of orthogonal, basically orthogonal complement. We had already studied during four fundamental subspecies, and I had already given a quick picture of four fundamental subspecies. Their orthogonal complementation was easy to visualize here. So after that, once I will discuss, I will come back to today's uh, part of lecture, important point, that how to construct orthonormal vectors, or simply I would like to say that orthonormal basis. I am much interested here to find orthonormal basis of a subspace in lower dimension, not generally in 2D plane. Even you can go to Rn as well. So in Rn also we can have variety of subspaces, one dimensional line. Also, line is a subspace passing through origin. So line is a one-dimensional subspace. If you take plane, plane is a two-dimensional subspace. If you take a space, 3D space, then 3D space is a three-dimensional subspace. Then those kind of things we can define it here. So what we will see that we will go term-wise. So if you suppose we are in R2, then what are the possible subspaces? So there are two possible subspaces, non-trivial subspace, two possible non-trivial subspaces in R2. What are those? Those are, sorry, there is only one trivial subspace. Why? Because only line is non only one non-trivial subspace is line. Why? Because two-dimensional subspace would be R2 itself, and zeroth dimensional subspace would be singleton set 0. So we are not willing to talk in detail about these two things right now in this example. And also, if we are taking your subspace complete R2, then this would be also a trivial subspace. Why? Because you can say that uh, Hello, are you able to listen me?
Yes, sir.
Again, there was some issue regarding connectivity. I need to share this slide here. So I was here. Slide is coming. Slide is visible. Anyone respond? Is it visible or not? Slide is visible or not?
Sir. Yes, sir.
I was asking question that what are the proper about, sir? So in R3, R3 itself is an improper subspace of R3. So that's way R3 would be improper subspace. It is a improper subset of R3. Similarly, if you take any line, or line happens to be two-dimensional, line happens to be one-dimensional subspace, and plane is a two-dimensional subspace. So these two are what? These two are proper subspace in R3. Why? Because definitely there exists at least one element in R3 which will be not in either in plane or in line. So that's why line and plane happen to be proper subspace in R3. And if you take its singleton set 0, then this one is a trivial subspace of R3. So here you can call these two are a proper subspace of R3. So that means any line passing through origin is a proper subspace of R3, or any plane passing through origin is a proper subspace of R3. Similarly, you can say that this singleton 0 containing only 0 element, so it is a trivial subspace. Trivially, it will be a subspace of R3. You don't need to prove many results. Automatically, this will be a subspace of any Euclidean space. So it's a trivial subspace of R3. R3. So in R3, if you go in R4, what are the possible subspaces in R4? So R4 itself, you will say that it is an improper subspace of R4 because R4 is equal to R4. R4. That's why it is an improper subspace. And every element of R4 is in the R4, and R4 is a linear space. That's why every in from that perspective, you can say that R4 is a subspace of R4 improperly subspace. What are the proper subspace in R4? Simplest, you take line, you can take a plane, or you can take a three-dimensional space. Take any three-dimensional space or three-dimensional subspace, any three-dimensional subspace. These are what? These are proper subspace in R3. R4, sorry. Proper subspace in R4. And what is the trivial subspace in R4? So trivial subspace, again, it would be singleton set containing 0. So trivial set in trivial subspace of R4 is singleton set containing 0 only. So you can say that this one is trivial subspace for every Euclidean space. Every Euclidean space, you can say that. But that improper and proper subset, those are very with respect to different kind of Euclidean subspace, and based on its dimension. So line is one-dimensional subspace, plane is two-dimensional subspace, 3D space is subspace is three-dimensional subspace in R4. So you are having three different kind of proper subspace in R4: one-dimensional, two-dimensional, and three-dimensional. But if you are in R3, you are having just two kind of proper subspace. One is line happens to be one dimensional, another one is plane happens to be two-dimensional. If you are in R3, you are having only one kind of proper subspace. What is that? One-dimensional subspace. That means line. You are having just line kind of subspace in R2. So those are the clear picture of proper and improper subspaces in Euclidean space. So that's way. So all these are lower dimensional subspace, easy to visualize, easy to handle. So most of examples where I need proper visualization, I will take it from these subspaces, these spaces. Okay, and at last I will give a recap. Sorry, I will give a hint how to proceed towards Gram Schmidt process. So coming to recap of last class, what I had mentioned that orthogonal complement or orthogonal projection, orthogonal complement, or we define it like this way. If we consider a vector space V in R n dimensional Euclidean space Rn with orthonormal basis U1, U2 up to UK. That means V is a k dimensional space. What is the dimension of V? Dimension of V is k. So dimension of V equal to k. And definitely, what is the relation between k and n? Definitely k would be less than n. Why? We are taking here and maybe less than equal to. So we are not. So here k would be less than equal to 1. K would be upper bounded by dimension of the Euclidean space Rn. So that's way. So if you take any arbitrary vector x from Rn, then we can project this x in two parts. One part is x parallel, that we are calling it projection of x in the given subspace V, and another part is perpendicular, x perpendicular. This will be perpendicular to the plane. Remember that it will act as a normal to the plane. This one, it will act as a normal to the plane. And how we find x parallel? We find it, we are saying that it is actually projection of x on the plane. And in last class, we had already seen that how we can calculate projection of a vector with respect to a subspace and with orthonormal basis. Here, very easy to calculate. We write easily because projection of x with respect to V, it would be, this vector would be in the subspace V. So this vector we can write as a linear combination of orthonormal basis of V. And when we are writing a linear combination, easily we can calculate this coefficient and it represents the orthogonal projection of x into V. Into V spanned by the vector U1, U2 up to UK. So transformation, this projection transformation, then it will imply that we know that if x belongs to kernel of T, and from the definition of kernel of T, it will say that T of x would be equal to 0. It is definition because x is coming from the kernel of T, and so it will imply that T of x equal to 0. And T of x is what? It is a projection operator. So that means T of x equal to 0. It implies that our parallel vanishing of parallel component. So parallel component, that's projection. That means projection component has been vanished if x is coming from the kernel of T. So it will imply that your x is equal to what? That means image of 0 is equal to what? X perpendicular. What does it mean? It simply says that every element from the kernel of T is perpendicular to the vector which are in V, vector space V. So kernel is defining orthogonal complement of given vector subspace V. So it is the definition. So definition I had already defined. So this V for capital V for, we are saying that it is orthogonal complement of V. It is defined in such a way, it is collection of all the n-dimensional vectors which are having which are perpendicular to V. Perpendicular to V means perpendicular to every element of V. So this perpendicular, how we define it? We define it by defining inner product equal to 0. So this is the definition of perpendicular vector. So and this capital V per we are calling it orthogonal complement of V. So one example I will give you here from the 4 fundamental subspaces. So you can see that if you are suppose you are taking V is a row space of this matrix, given matrix having column first column 1 3 second column 2 6. Then suppose we are taking this one as a vector subspace. Then what would be orthogonal complement of this one? Try to see that this is so this column row space of A is what? It is a line. And what is the thing? What kind of a space which is perpendicular to this one? So this is the space perpendicular to this one. If you take any vector from this line, that would be perpendicular to this line. So that's why here null space of A, we will call it D per. That means orthogonal complement of row space. Similarly, if you are in target space or codomain space, what is your suppose you are taking column space as your subspace, then what would be D per? D per would be left null space. You can observe that here D per is left null space. So here you can observe that if you define a Minkowski sum between D and B per here in this example, what you observe, it is equal to R2 in both cases, in domain cases, also in target cases. So you observe this kind of relation. So that's way it is. I'm not saying projection. You are able to decompose every projection part. Another part we are calling it perpendicular part. That is the scenario of looking orthogonal complement. Now coming to construction of orthonormal vectors in a plane. Before plane, I will talk about construction of orthonormal vectors in a line. With respect to line. That one is a very trivial job. So that's why I haven't treated. So consider a subspace V in R2. So suppose V is a proper subspace, then it would be a line. That means if V is a line, then line is having only one direction, and that would act as a basis. You can say that line is having a basis with single element. So this V1 is the basis of this line as a subspace, and we can find orthonormal basis U1 how? Just by dividing the norm of V1. So this one, you know that if you divide any vector by corresponding norm, then that vector becomes a unit vector. So geometrically you can observe that like this way. If you're taking just a line, so this is line. Right now, not focus about this. So this line you are taking it. This is the line having basis V1. V1 is the basis of this line. So how can you find orthonormal basis of line? You need to divide V1 by norm of V1, and you are getting U1. U1 is the orthonormal basis of this line. U1 is the orthonormal basis of this line. This is the idea of getting orthonormal basis in line, because line is having only one basis element, so it is a very trivial job. So it doesn't look into much more intuitive here, regarding orthogonality. So we will go to plane. So if you take a plane that means complete R2. Then what is happening? Definitely it will have a basis, and this basis we are taking a non-standard basis V1 and V2, and there would be two elements in the basis because V is now here V we have taken as a plane. That means V equal to complete R2. So in basis of V we will have two vectors or two elements V1 and V2. Now based on this information, we are having this information. Based on this, we will try to construct orthonormal basis U1 and U2. So just now onward, remember that whenever I am taking the basis notation and if I represent by UIs, then you can simply assume that those are representation for orthonormal basis. And when I am representing basis element by VI, then you can say that those are representation of non-standard basis. And here UIs are representation of orthonormal non-standard basis. So these are to convert this basis, this non-standard basis into orthonormal non-standard basis. How we can do? So I will talk about few steps. So there we will perform 3 steps. First step, what we do? First we construct. Just order is very important. So first we will get first unit vector. How we can get first unit vector? Divide V1 by norm of V1. Then definitely it would be a unit vector. We got the first unit vector like here what we have already got. So this is the first step. Next step, what we will do? This next step is very important, and you can say that it is a very crucial step. So in step 2, we have to get U2. So we have already seen U1. Now we are trying to construct U2 in such a way U2 has to such that satisfy 2 conditions. First condition is that U2 must be orthogonal to U1. That means dot product of U2 with U1 must be 0. And apart from that, norm of U2 must be 1. So two things we have to look into here. They are going to be 1. So that is the to U1, because you can observe that this one is V1. You can say that this one is V1 and this one is V2. So there is an angle between acute angle between V1 and V2. Definitely V1 and V2 are not perpendicular to each other. Now we have already got in a step 1 U2. So how we can get? So remember that decomposition that you decompose V2 into part. That means project V2 along the line. So that would be this V2 parallel. It would be that is projection of V2 along the line. It would be in the direction of U1 is orthogonal part of V2 projection. So this is V perp, V2 perp. So V2 perp is always perpendicular to the line. So if it is perpendicular to the line, then definitely V2 perp would be also perpendicular to the vector U1, unit vector U1. Why? Because U1 is the direction of V. So we observe, if you try to find simply dot product between V2 perp. Remember, not try to find dot product between U1 and V2. Try to find dot product between V2 perp and U1. Then definitely the dot product would be 0. Why? Because from the geometry also it looks V2 perp is perpendicular to U1. So that's way. So we got a perpendicular. So we have already from here we have already got V2 perp. What is that? This one V2 perp, you can just do little bit manipulation. So V2 perp is what? V2 minus V2 projection of V2 along U1 or along the line. So we know that from the projection representing projection in terms of unit vector. So we can represent this term as what? What is this one? This one is just you can write like this way. Projected part, that would be what? That would be nothing. Just it is talking about inner product of V2 with U1 and this projected part. This one is in the direction of U1. So that's why you are multiplying with U1. So this V2 minus dot product of V2 with U1 times U1. This it is directly you are getting what? It is your V2 per. Because orthonormal factor happens to be unit vector, so you have to normalize. So that means you have to reduce the norm of V2 perp. And then that representation would be we will call it U2. That it then it becomes U2. So here you can observe that you got U1. U1 is also unit vector, and U2 is perpendicular to U1. Apart from that, U2 is also unit vector. So in the third step, this is the third step what I discussed. So in third step, what we will do, we will divide a V2 curve by its length or norm of V2 curve. Then we will get U2. So this is the story. So U2 is what you can observe that the angle between U2 and U1 is what now 90 degrees. So you can establish that condition here, that how U2 is perpendicular to U1. So it is just consider as a homework. You can try yourself and easily you can establish that. So just very fast forward, I will take one example of whatever I discuss. I will take one example based on that discussion. So suppose we are having a two-dimensional subspace in R4. Suppose we are taking a two-dimensional subspace V in R4. This one is, you can, why? Because it is a linear combination of only two linearly independent vector. So definitely the basis of V is having only two vectors. So these are the basis, and this basis what are basis V1 and V2? What are these? These are definitely, we can say that the dot product between these two are not zero. You can find dot product between these two. What would be dot product of V1 and V2? So we can say that V1 and V2. First, we can say that these two are non-ascending basis. Second, we can say that V1 and V2 are not orthogonal to each other. So we have to construct an orthogonal basis from V1, V2. How we can construct? So this process I have discussed it here. First, find the inner product between V1 and V2. What is the inner product? 1 times 1, 1 times 9 plus 9, or 1 times 9 again plus 9. 1 times 1, that means 1. That means total sum is coming 20. That one is not equal to 0. So simply we can say that V1 and V2 are not perpendicular to each other. So that guarantee is directly coming from the inner product. The next, so we will convert this one into U1 and U2. U1 and U2. So that would be what? That would be orthonormal basis. How we can do? So easily you can get U1 how? By dividing V1 by its norm. So what is the, it is coming? So square root of 4 is what? 2. So norm of V1 is 2. Or length of V1 is 2. Euclidean length. So we divide, when we are dividing this vector by norm of V1, then we are getting this vector. So you can easily say that if you are willing to find norm of this vector, it would be 1. So we get first unit vector. Next, we are trying to find a orthogonal vector which is orthogonal to U1. So how we can find? Using this concept. Like we will find a V2 per. So V2 per we will find how? So V2 minus inner product of V2 with U1 in the direction of U1. So just simplify this one. So this one is V2 minus, if you find inner product of V2 with U1, what would be that? That would be 10, and you multiply with this vector in the direction of U1. So simplified V2 perp is coming this one, this vector minus 4, 4, 4, minus 4. Okay, so this one is not a unit vector. So next concept, that means this you can say that it is a step 1. This one is a step 2. And in a step 3, what you do? Perform normalization. Normalize V2 per. That means divide V2 per by its norm. So what is norm of this V2 per? V2 per norm is 1 by 8. So if you divide by 1 by 8, you are getting this vector. So easily now you can see that here U1 is a unit vector, U2 is also unit vector. And if you are willing to find dot product of U1 and U2, what would be that? Definitely it would be 0, because we have done construction in such a way geometrically everything is visible. So let us try to check algebraically as well. So if you try taking dot product or inner product of U1 with U2, what would be inner product? So 1 by 2 times minus 1 by 2, that is 1 minus 1 by 4. 1 by 2 times into 1 by 2, that means plus 1 by 4. Then 1 by 2 times 1 by 2, that means plus 4. And last one coordinate is saying 1 by 2 times minus 1 by 2, that means minus 1 by 4. If you sum it up all these components, what is the result? The result you are getting is 0. That means u1 and u2 are perpendicular to each other. Also u1 and u2 are orthogonal to each other. So you can say that you got your orthonormal basis based on given basis B1 and B2. So you got your desired orthonormal basis. Now we will talk about is there any relation between basis B and basis A? That means basis B is any non-external basis and basis A is the orthonormal basis. So is there any relation? So we will see the relation as well. So how these two are related to each other? So we have already, this one is the orthonormal basis. So what we will do here, we will find change of basis matrix. We call change of basis matrix. So what is change of basis matrix? When your direction is fixed from, that means you are going from non-external basis given basis B to orthonormal non-external basis A. This is the direction. So in order to find that, how you are doing it, that what you do, take all the bases and find the coordinate of all the bases with respect to new basis. Your new basis is what? Orthonormal basis. So find the coordinate of all the bases with respect to new basis. So V1 is the coordinate of U2 calculation is very simple, easily you can find. That means you are saying that V1 you are trying to write as a linear combination of U1 and U2, and here you don't need to solve a system of linear equation. Why? Because here U1 and U2 are orthonormal in nature. So that's why just using the concept of dot product, easily you can get alpha 1. What would be your alpha 1? Alpha 1 would be just dot product of V1 with U1. So if you perform dot product of V1 with U1, what you will get? Dot product of V1 with U1, you will get here 2. Similarly, if you find dot product, how you can find alpha 2? Alpha 2 you can find easily, perform dot product of V1 with second orthonormal vector U2. So what would be this value? This would be definitely 0. So you can try this calculation. Just for simplicity, I am writing directly because I am very near to 45 minutes. So I have to wind up this class. Similarly, you have to express all the bases in order to find a coordinate vector of V2 with respect to new basis. So we will express all the basis element V2 as a linear combination of new basis. So call it beta. Alpha 1, alpha 2 I have already taken. So the next notation I will take beta 1. Beta 1 times U1 plus beta 2 times U2. So how can you find beta 1? That is first coefficient of V2 with respect to U1. So just take dot product of V2 with U1. So dot product of V2 with U1. It will value would be 10 because you are having already V2. You are having also U1 U2. You have already constructed. Now what would be beta 2? Beta 2. So if you simplify dot product, it will come as 8. So you got first column of this change of basis matrix R, and you may ask one question that why I have taken notation relation R in place of S. This R will define this change of basis matrix. It will define orthogonal QR decomposition. So that's why Q would be orthogonal matrix and R is a upper triangle matrix. So you can observe that this one is upper triangle matrix. So due to that we are taking a specific notation. So this one is a change of basis matrix from where to where, from a non-standard basis to corresponding orthonormal non-standard basis. So you got the change of basis. Now, do we have any relation of this R with this basis element and old basis element? Yes, we are having. So that relation here I will talk here. So relation is that. So if you construct, so relation is directly coming from the relation between the coordinate of old coordinate and new coordinate. So if your direction is here like this way, you are going from B to A. That means basis B to A you are going. That means, or if you take any vector x, then what is the relation of coordinate of this new coordinate of x? That means coordinate of x with respect to A with coordinate of x with respect to all bases. What is the relation? That relation we always relate it by what we call it change of basis matrix. We relate it by change of basis matrix. So those things are coming here. So change of basis matrix will come into picture. So this relation, either inverse or change of basis matrix. So here if you are going to B to A, so you have to define change of basis matrix from B to A. Okay, and if you are going from A to B, then converse, you can revert it. You can take inverse and vice versa. So similar thing I am saying it here. So you collect, define a matrix having first column from V1 and second column V2. Call this matrix M, and define another matrix where first column is coming from orthonormal basis U1 and second column from orthonormal basis U2. If you multiply Q with R, then you will get M. So M is any given it is a matrix with respect to given basis, and Q is matrix with respect to orthonormal basis, and R is the change of basis matrix. So this so simply we can say that we have decomposed M into two factor matrix. One factor is coming Q, another factor is coming R. So this factorization or decomposition. Another name, you can say that you are able to write matrix M as a factor of two matrix or product of two matrix. So this you can say that factorization or decomposition also. So what is happening? What is the nature of Q? So Q has a very interesting nature. What is the nature? If you take dot product between column, then dot product is 0. That means you are saying that column of Q are orthogonal to each other. Apart from that, if you are willing to find norm of columns happen to be unit vector is 1. So columns of Q are two criteria. First is column of Q are orthogonal to each other. That means C1, inner product of C1 with C2 is 0. And second criteria is what? Second criteria is the norm of both the vector or length of both the columns are unit. So this kind of a special matrix, so we are giving a special name. This matrix we are calling it orthogonal matrix. So from high school you might have already seen two example of orthogonal matrix. So also we had already seen that one orthogonal matrix in prior. That matrix was change of rotation matrix. So what was the rotation matrix or matrix of rotation transformation into R2 to R2? It was we denoted by cos theta minus sin theta. This matrix is a famous rotation matrix, and that means if you multiply any coordinate with this matrix, then coordinate will be changed by an angle theta in anticlockwise. So this matrix we are calling it rotation matrix, and also you might have already seen this example in coordinate geometry as well. So this matrix we are calling it rotation matrix. So what is happening? If you try to look this matrix, then what is a relation? It is a orthogonal matrix. Why? If you are willing to find norm of column, what would be norm of first column? It would be cos square theta plus sin square theta. Summation of cos square theta plus sin square theta is what? 1. That means norm of first column is 1. Similarly, norm of second column is 1. And if you are trying to define dot product between these two columns, that would be also 0. So that's why this matrix we are calling it orthogonal matrix. Orthogonal matrix. It is